Hey everyone, in this video I take you through the full workflow starting with 3D scanning this 1000 square meter seafood restaurant and then turning it into a complete floor plan. And for this project I'll be using the LiGrip O2. Right now it's the best SLAM LiDAR scanner you can get. I'll be scanning both the indoor and outdoor area in a single pass. Initialization on the O2 takes about 30 seconds. During that time, I'm pointing the scanner toward the high feature area, the building in the front. This is a real commission project. The restaurant is about to undergo renovation, and the architects brought me in to handle the LiDAR scanning. There weren't any as-built drawings available, and with all the dense vegetation, it was really tough to pinpoint the property boundary. A total station can't handle this kind of obstruction, and a drone LiDAR won't work either with so much tree coverage. Moving into the sushi bar, you will notice these large mirror panels. They create ghosting on the opposite wall, and later I show you how to remove those artifacts. I walk in a small loops to boost accuracy and eliminate blind spots. The architect already knows to work with 3D scan point cloud data, so instead of submitting a CAD 3D model, I just convert the scan into an RCP file and they will continue the design in Revit. For smaller rooms like this toilet, I just stand at the entrance for a few seconds. There is no need to go inside. I'm not using RTK for scanning today because the N-Trip network went down again, and since it's Saturday, it probably won't be back online till Monday. I walk up here to scan the wall line and also capture the load width since that measurement is required for the building permit. I'm walking into the restaurant's main building. I didn't leave the door open this time because the place is already open for service. Those two women on the left are the architects. I actually worked with their parents years ago, and now I'm collaborating with the next generation. Again, I walk in loops wherever possible to improve accuracy and eliminate blind spots. Now I'm heading into the kitchen area. Now this looks like the pantry. And here's the kitchen. When exiting through a narrow doorway, I walk sideways to keep the scanner aligned. If a room has more than one door, you should exit through a different one to create a loop path. Now I'm heading back to the starting point to complete the scan. The scan took 11 minutes, covering a trajectory of 415 meters. Next, I will transfer the scan data to the PC using a USB-C cable. The transfer speed is fast at 160 MB per second. Green Valley will soon launch its cloud processing service. It's currently in testing, but once it's ready, you won't need a PC anymore to process point cloud data. It will come with a fee, though the exact details aren't ready to be revealed. This is LiDAR360 MLS, the post-processing software used for colorless point clouds and 3D visualization. After naming the project, simply select the project file from the scanner and press Start to run Point Cloud Fusion. Here is the colorless point cloud result along with the walking trajectory. You can see I have created several closed loops in the path. Each time the software detects a closed loop, it eliminates drifting errors, resulting in a more accurate scan. The software took 61 minutes to process the 11-minute scan data. Here is the accuracy error report. It shows that over 98% of the capture area has less than 1 centimeter of error. The scan output in LAS format is split into two files. I will import them into CloudCompare to merge, crop, align, and remove mirror ghosting. First, I select the two point cloud segments in the browser and click Merge. From the top view, I use the segment function to crop only the necessary data. Then hit on the Delete key. Okay, let's check the cross section. The result is excellent. It produces a sharp, unblurred, colorless point cloud indicating high precision scan data. With the rotating LiDAR sensor, there are virtually no blind spots on the floor. From this scan data, it's straightforward to generate a CAD model. Even with the wall painting, the scan looks sharp and highly detailed. The drain pipes are clearly visible in the scan and easy to trace. This cross-section perspective provides the architect with design inspiration. You won't be able to reproduce this with other survey tools. This ground point is at negative 8.96 meter, so I will use the Translate tool to move it forward and place it on the origin XY plane. Next, I will save this point cloud as a single LAS file for importing into AutoDesk ReCAP. The file conversion takes less than a minute and the scan data is now deliverables. The architect I'm working with already knows how to create CAD models from scan data, but locating the property boundary and the column center line is a bit tricky and requires experience, so I will assist them with this task. Here's in BricsCAD. After cropping the point cloud floor area, I begin tracing the property boundary. And this side of the wall is completely blocked by trees and buildings, but some sections are partially exposed, allowing me to trace the full wall line. From the top view, I'm locating the column center lines and found that the bay width measures 5 meters. When I offset the line by 5 meters, it lands exactly at the center of the beam. In the kitchen area, the columns have a narrower span. When I offset the beam center line by 7 meters, it lands exactly at the beam center. So the kitchen bay width is half of 7 meters or 3.5 meters, and it matches the scan data. Next, I trace the line along this side of the wall and offset it to determine the building's width. Some sections of the outer wall are exposed behind the trees. Next, I simply trace the remaining walls. Some internal walls don't sit at 90 degrees. This isn't a scanning issue, it's a construction error. Since the scanner's already been fully tested, I'll stick with the scan data. Next step is tracing out the portal frame geometry. If you are interested in learning 3D scan to CAD using LiDAR Scanner and BricsCAD, I have created a course on Ko-Fi. The link is in the description. From here, I can even detect the depth of the purlins, which is 100 millimeters. And here's a cross-sectional profile of the portal frame. When the door is closed, it's difficult to identify its location from the cross-section. Instead, you need to use the color point cloud to locate it. There is also a small awning outside, supported by columns. Here's another closed door that must be located using the color point cloud. Here's the sushi bar. I'll start by tracing the line along one side of the wall and then offset it. There's some part of the wall that is still visible and I can use it for alignment. I use 100mm for the width of the wall. Moving on to the toilet area. You can clearly see that the toilet building walls are not rectangular. So I need to follow the scan data. There's one more storage room here, and there is also propane gas tank storage area. Next, I place the parking lot traffic marking. Next, it's time to identify the floor level. I'll use the point ID command and snap to the point I want to measure to get the floor elevation. That's it. This is the floor plan created from the LiGrip O2 scan data. If you are planning to generate multiple cross-sections and projection views, I recommend modeling in 3D CAD as it's faster, but for this project, I only need a single floor plan, so 2D CAD was the quicker option. I also brought along the Pocket 2 to scan for 3D.js since it offers a cloud service I can share directly with the architect. For comparison, this is a 3D.js from the LiGrip O2. I set it to the medium setting, run on my PC for 3 hours and 20 minutes. And this is the result from the Pocket 2. The data was generated from the online service. They must have made some changes because now the 3D.js from the Pocket 2 shows a lot of jelly effect. Meanwhile, the O2 produces much higher detail. Okay, let's move here. And here's the result from the Pocket 2, from the O2, and the Pocket 2. Okay, let's have a look in this angle. And this one from the Pocket 2. I really don't know what caused the jelly effects on the Pocket 2. And the web browser based 3D.js viewer from the Pocket 2, it has wall detection. So sometimes I cannot get into the building. Okay, this is the look from the interior of the restaurant, the Pocket 2. And here's from the LiGrip O2. It's much better than the Pocket 2. And here's the sushi bar from the Pocket 2. And here's from the LiGrip O2. Now switching back to the LiGrip O2. It's much better in the low light condition. With these results, I will submit the 3D.js output from the LiGrip O2 instead, even though it doesn't provide a cloud-based service for viewing the data. But the 3D.js has become essential for architect clients. Once clients have used 3D.js, they will always ask for it. I don't need 3D.js to create a building model in CAD. The colorized point cloud is sufficient, but for most architects, 3D.js provides more complete information as a design aid. So I need to find a way for my clients to view the 3D.js offline without requiring a large software installation. Then I found a free 3D.js viewer that requires no installation, and the software is only 40 MB. It's called 3D.js viewer, and I'll include the download link in the description. To use it, simply drag and drop the PLY file that was converted from LiDAR360 MLS. You can navigate with the WASD keys on your keyboard, but note that there is no compatibility with Space Mouse. The default setting use Y-axis up, so you will need to rotate the model in the transform tab along the x-axis by 90 degrees. The navigation isn't as smooth as the LiDAR360 MLS viewer, but it's still good enough for use in design meetings. Here's my complete workflow from LiDAR scanning with the LiGrip O2 to producing a floor plan. Thanks you guys for watching. I'll see you in the next video.